All right, this is AP, AB, and BC Calculus. We're doing Unit 8, Section 5, which is finding the area between curves expressed as functions of y. So this is the same basic process as the last video, but instead of a top minus bottom, we're going to be doing right minus left. So when we have functions in terms of y, not x, finding the area between the curves by doing top minus bottom wouldn't make sense because top minus bottom would refer to the y value that is higher than the other y value, right? Top means higher y over bottom, which is lower y. Well, when we're integrating with respect to y, instead of x, we're going to do the top x value, which would mean farther to the right, minus the bottom x value, which would be farther to the left. So basically, instead of top minus bottom, it's right minus left. So it's the same concept, larger function minus smaller function. So here, if we were looking at this area, this green area here, right, we have this red parabola, which we're calling g of y, right? We have this blue line, which is going to be f of y. So if we wanted to find the area, we would do the right curve, which in this case is the blue line. It's physically to the right of the red curve. So the right thing, which is the higher x value, minus the left thing. So here, we're going to integrate f of y minus g of y with respect to y, but the bounds also have to be y's. So if you notice, the points of intersection happen when y is -2 and when y is 4. We're going to do the lower bound, which is the physically lower y value, -2, up to the higher bound, which would be the 4. All right, so let's go ahead and walk through some examples. So we're going to try this without a calculator. We're going to find the area between so 3 root y and 2 root y from 1 to 4, right? So again, I'm not really setting you up here for ones that are going to crisscross. We're going to talk about that in a later section. If you were trying to figure out what this image looks like, right, it can be kind of helpful to graph this. So if you were trying to figure out what 2 root y looks like, right, so remember here, you're plugging in y values, not x values, right? So there's 5, 1, 2, 3, 4, 5. Okay, so let's just look what happens if we plug in some values here, right? So if I plug in f of 1, right? F of 1 means plug in 1 for y. I get a value of 3 root 1, which is 3. So if I plug in f of 1, and I think most of us this is not super intuitive, so that's why I'm walking through it, I get 3. What that means is that when I plug in y is 1, I get x is 3, right? So when I plug in y is 1, I get the point where x is 3, right? If I wanted f of, let's say, 4, because that's the other endpoint, right, I would plug in 3 root 4. I'd get 3 times 2, so I'd get 6. But remember, we're plugging in y values in these functions and getting x values out. So when I plug in y is 4, I get an x value of 6. So 4 and 6, okay? So essentially what's happening, and I think you probably are comfortable with knowing what a square root of x graph looks like. Square root of x, right, so square root of x looks like this. Square root of y is going to look, sorry, my bad, is going to look like this. It's going to look like half of a parabola, essentially. And you could see that if you plugged in if you plugged in 0 for y, you'd get 0 for x because the square root of 0 would also be 0. So this is essentially what my f of y looks like. If I wanted to know what my g function looks like, right, so g of 1 would be 2 root 1 or 2, meaning if I plug in a y value of 1, I get an x value of 2. So y value of 1, x value of 2, right? And if I plug in g of 4, that's the y value I'm plugging in, I get 2 root 4, which would be 2 times 2 or 4. So when I plug in 4, I get 4, which is here. So, and this both graphs start at 0, 0, because again, if you plug in the square root of 0, you get 0. So this is my g of y. If I want the area that I get from where y is 1, which would be right here, to where y is 4, this is the area that we're talking about. This red area is the area we're talking about. In order to find that, so what I want you to note is that f of y is the right curve. So the area that I'm asked to find, right, is going to be the integral from the bottom y value, which was 1, despite my terrible graphing, to the top y value, which is 4, so from 1 to 4, of the right curve, which is f of y, right, minus the left curve, which is g of y with respect to y. Now, since this is a non-calculator question, I'm going to be gutting this out by integrating by hand, so good times. So an interesting thing here, though, you can actually make your life a little easier because 3 root y minus 2 root y is just a root y, right? They're both root y, right? That's 3 of something minus 2 of the same thing. So you could make this the integral from 1 to 4 of the square root of y with respect to x. So when you integrate, that's actually a y to the 1/2, right? So you're going to up the power by 1, which would be 3/2, and divide by the new power. So you're going to get 2/3 y to the 3/2 evaluated from 1 to 4, which means you're going to get a 2/3, and then you're going to get 4 to the 3/2, which we'll talk about in a sec, because you might be rusty at that, minus a 2/3 times a 1 to the 3/2. 4 to the 3/2, so just putting this off here as a note, because I think sometimes we get rusty at this skill. 4 to the 3/2 is either the same as a 4 cubed in a square root, or it's the same as the square root of 4 quantity cubed. 2 cubed is generally easier. Now, either of them work in this case because we know the square root of 64 is also an 8. But this is usually the better option to get to that value. So I'm going to get that this is 2/3 times 8 minus 2/3 times 1. I think that's a 2/3 times a 7. So I think our answer is 14/3. So I think the answer is 14/3. Now you might be saying, okay, cool, Hogan, but how on earth am I supposed to check this in a calculator because everything's in terms of y? Well, the answer is you cheat and you pretend y is x in your calculator. So basically, you cheat, and in your calculator, you're going to put 3 square root of x instead of y, and you know in your head that that x stands for y, but your calculator can't integrate with respect to y. And then you're going to do 2 square root of x, right? And then you're going to integrate, so you're going to do math 9, right? And you're going to integrate vars over to y vars. But again, you know it's not y, but your calculator doesn't know that. So here we are. So y1 minus y2, comma, with respect to x, even though you know that that x is actually a y, from 1 to 4. And then you're going to go ahead and math bracket, and there's your 14/3, okay? So again, when you're integrating in a calculator, even though you're technically integrating with respect to y, you're using an x in your calculator, and you kind of need to know that. All right, so let's keep moving. So we're going to find the area between f of y and g of y from y equals negative pi over 6 to pi over 6, and we need to look and see what these curves look like. So I get that you probably don't feel super comfortable about what a sine and a cosine look like when they're on the y-axis, which is fine, right? We're gonna practice what this looks like. But basically, if we're graphing this on the y-axis, so, oh, my bad, terrible drawing straight lines. So if we were trying to graph this, right, the easiest way to do it is to just plot a couple of key points that we know between negative pi over 6 and pi over 6. There are other options, but it's genuinely the easiest thing to do. So, so we know that sines and cosines oscillate between 1 and negative 1, and that's, remember, this is x equals negative sine of y. So the x is the output, right? The x is the output, the y is the input. So basically, if I were you, I would just pick a couple easy y values that fall in between these things, right? And you could literally just make a table that finds g and f to find easy values. Now, this is assuming you literally have no calculator. So you probably will have a calculator in most situations, even if you're not supposed to use one. I'd rather you do the academically honest thing and don't use it. But in some situations, you're allowed to use a calculator but are asked to show work by hand. Well, that's a situation where you could definitely use the calculator to see what this looks like. But again, it's a little tricky because you can't really graph in terms of y in your calculator, so you'd still be graphing in terms of x. So if I want to see what this looks like, I know I'm supposed to start at negative pi over 6. I know the other important values on the unit circle. I know the only one that really falls in the middle between negative pi over 6 and pi over 6 is 0. Like if you think about where these live on the unit circle, like if this is my unit circle, here's pi over 6. Here's negative pi over 6. The only significant value on the unit circle that falls between them is 0. That's really literally it. So if you were trying to figure out other important values, you're pretty much stuck with 0 right now, right? So so if we go ahead and put this in here, right? So the sign of negative pi over 6, that's going to be a negative 1. The negative sign of negative pi over 6 is going to be a positive 1/2, right? Because the sign right here should be a negative 1/2, but there's a minus in front, right? Similarly, the negative sign of pi over 6 should be a positive 1/2, and anytime you plug a 0 into a sign, you get a 0. So that's what we've got. So if I were trying to graph this, and notice that my y values that I'm plugging in are literally pi over 6's, like negative pi over 6 and pi over 6, and that's fine because that's like I just need a rough idea of what this looks like. This graph so here's my negative halves and my positive half, right? So when I plug in negative pi over 6, I'm supposed to get an x-coordinate of 1/2. Then when I plug in 0, I get 0. When I plug in pi over 6, I get negative 1/2. So this graph, like, and it doesn't have to be perfect, but it looks something like this, right? It looks something like that. If I then do the same thing for g, right? So let's go ahead and plug in the g function, right? So g is 2 cosine y. So if we look at the cosine at negative pi over 6, the cosine of negative pi over 6 is a root 3 over 2. We're doubling that, so this is a root 3, and we'll deal with that in a second. So I should have given myself a little bit more room on the axes, but we'll survive. 2 cosine of 0 is just a 2, and when I plug in 2 cosine of pi over 6, that's also a root 3. So basically what's happening, if we give ourselves a little bit more space here, so here's 2, and then root 3 is like a 1.7. So just so we're clear, root 3 is somewhere around there. This graph is going to look something like this. At negative pi over 6, we have a root 3, then we have a 2, then we have another root 3. So this graph looks something like this. That's all we're seeing, right? And so the window that we're talking about when we talk about the area, since these are my bounds, this is the window we're talking about. We really don't care what happens to the graph beyond that. Like, that's the only area we care about. So the work we need to show is that the area we're trying to find is the integral from negative pi over 6 to pi over 6 of the blue function, which was g in this case, right? So g of y minus f of y with respect to y. Now, if this is a calculator section, I can just type it in and integrate, but sadly it's not, so we're going to go ahead and do the work to get there. So the work is going to be the integral from negative pi over 6 to pi over 6 of g, which is 2 cosine y, minus a negative sign, so we'll say plus sine y with respect to y. We can integrate those by hand, so we're going to get that this is a positive 2 sine of y minus a cosine of y, and we're integrating from negative pi over 6 to pi over 6. So when we plug in pi over 6, right, we're going to get a 2 times sine of pi over 6, which is a 1/2, minus cosine of pi over 6, which is a root 3 over 2. That's the top bound. Minus, when we plug in negative pi over 6, we're going to get 2 sine of negative pi over 6, which would be a 2 times a negative 1/2, right? Minus the root 3 over 2, because cosine of negative pi over 6 is the same. So I'm going to end up getting that this is a 1 minus a root 3 over 2. This is a negative of a negative 1, so that's plus 1, plus a root 3 over 2. The root 3 over 2's cancel, and after all that work, my answer is 2. Excuse me. All right. So now this is a calculator problem. So, I should go back and check this one in the calculator. My bad. Oh, sorry. Skipping back up. There we go. Sorry, I skipped the question. All right. So I should go back and check this in the calculator. Remember that when I check it in the calculator, I'm going to cheat and I'm going to use x's. So to be perfectly honest, I don't know that it's worth my time to put this into my calculator as y1 and y2. So I'm just going to check it in my calculator by going to math 9. Right, and remember, I'm using x's even though I know that they're y's, because the calculator doesn't care what letter's what. They just care, it just needs me to put the correct variables with respect. So if I say with respect to x, it just needs x in that spot, right? So with respect to x, from negative pi over 6 to pi over 6. And then you should double and triple check that it's right, because again, so many times we just type something wrong. So function integrate, 2 cosine of x, but x is standing in for y, plus sine of x with respect to x, but again, all those x's are actually y's, from negative pi over 6 to pi over 6, and I hit enter, and there it is, it's a 2. All right, so here we go. So this is my little spiel that I've already been telling you. So in your calculator, you're not going to be able to use y as your independent variable. It's not a big deal. So the reason I didn't mention it till now in the slides is technically you weren't using a calculator on these questions, right? But I'm telling you, you should pretty much always check your work on a calculator anyway. So we do this all the time already. When you use x of t equals 5 cosine t, or v of t equals 5 cosine t or something else, you always use x in place of t and you never think anything about it, right? So here the difference is that x is in place of y. You don't write that for the AP, you don't communicate that with others, just like you wouldn't use an x on the AP if you were using x in the place of t in your calculator. The biggest issue is that people tend to get confused if you're not paying attention. So you just have to remember that even though you're putting it in as a y or as an x in your calculator, it actually represents y. So on the calculator sections, you can still use that absolute value trick that we've seen where it doesn't matter which curve is to the left or right. Because it, just like we saw before where it doesn't matter which curve's on top or bottom, you could use the trick on a calculator section where it doesn't matter which curve's left or right, because again, if you absolute value the whole thing, it won't matter. So, all right, let's go ahead and find the area between f and g. So I don't have bounds here, right? So the trick is that I'm going to have to graph this in my calculator and find the bounds, and I'm going to have to remember that I'm graphing it in terms of x, but my x means y, and that's confusing, and I get that. But that's the reality of how we use our calculator. So I do natural log of x knowing that those x's in this problem that I'm now entering here represent the y, which is, again, kind of backwards feeling, but you'll manage. It's one of those things you get better at as you do it. So remember, x is standing in for y and y is standing in for x. So when I graph, anything I get out as an x value is actually y in the problem that I'm doing on the paper, okay? So the first thing I need to do is I need to find the intersections, right? I need to find the intersections because those are my bounds. I wasn't given bounds, which means that in order to find bounds, I have to find them myself. So I'm gonna go ahead and graph, right? Okay, so there's one intersection, I can't see both. Now I wasn't zoomed 6 because we did other stuff. Hey, there it is. Okay, so the trick is, this isn't what the real graph looks like. This is actually the inverse of the real graph. The real graph would be sideways. So again, remember my x's are y's and my y's are x's. So second calc intersect, right? And I'm gonna scroll to where they hit each other. And remember, I want the x values, but they're not x equals, they're y equals. So I want this x, right? So the one bound is going to be y is approximately 1.47423333, right? And I'm going to store that as a, right? So even though I picked the x value, that's because remember, x's are y's in my calculator. So I'm going to call that a. That's my a, dot, dot, dot. And you can call C if you want to use C and D for Y values instead of A and B, it doesn't matter. So I'm gonna quit out of this and I'm gonna go ahead and hit that X and I'm gonna store it as alpha A, okay? Because remember we made that mistake before and we don't want to. So then I go back to my graph, I second calc intersect, which is 5. And I hit enter. And then I get that the other one, the other Y value where they intersect, is approximately 6.1573267 dot dot dot, and I'm going to call that B, and I'm going to store it as B for my own benefit, right? So I'm going to quit out of this. So second quit, I'm going to do X, and I'm going to go ahead and hit store alpha B, okay? So it doesn't matter which one, what letter, you could call them C and D, you could call them any letters that are not X's or Y's or somewhere else in the problem. So don't use F or G or X or Y. Cool. Okay. So I've got these values, right? Now the issue here is it's very hard mentally to see which curve is technically on the top, probably in your brain, because this isn't what the graph looks like, right? The graph would look like a line that is flipped over the line y equals x, and that's a weird feeling, right? It actually turns out it's still the same curves that you'd expect. Like if you flipped this thing over the line y equals x, the curve on top is the natural log curve, right? And the curve on the bottom is the quadratic. If you flipped this over the line y equals x, the curve on the right would still be the natural log curve, and the curve on the bottom would be the left would be the quadratic. So you can intuitively figure it out that way, but to be perfectly honest, it really doesn't matter, because remember, I'm allowed to use an absolute value. I'm allowed to say that the area is the integral from a to b of the absolute value of f of y minus g of y. I can say the absolute value because then it doesn't matter which way I integrate. Honestly, in this case, I can tell that f of y is going to be the bigger one because, again, if you flipped this over the line y equals x, if you were to reflect it over, you would see that the natural log is the one that will be on the right. But it doesn't matter because all I have to do is write that integrand. So this is what the AP needs. They need me to find these values and make sure I call them y. They need me to communicate this is how I'm going to integrate, and then they need typey, typey, type, here's your answer. So I'm going to go ahead and quit out of this. I know that this, so I know that this is the one I called y1. Again, that's my notation, not the calculator's not the AP's notation. I know that was my y1 and y2, but again, it doesn't really matter because I'm about to absolute value them anyway, so as long as the AP sees this notation, it doesn't matter. So I'm going to hit math 9, right? I'm going to go ahead to math, number, and pick abs, and then I'm going to go to vars, y vars. Again, it doesn't matter which order I do them in because I'm absolute valuing, so nobody will know. It won't matter. Close the absolute value, comma, with respect to x, but remember x is standing in for my y, comma, alpha a, comma, alpha b, okay? And I hit enter, and there's my answer. So I get that it's approximately a 14.465, or 6, depending on if you round or truncate, and remember, you're only rounding or truncating on the final answer. So the heavy lifting here is that you have to know what the integrand should look like. You have to know what integral to use, what the integrand looks like, and you have to find the actual values of those bounds. All right, so go ahead and try P2 without me. Give it a try, pause me, see what happens. All right, I'm gonna go ahead and start. If you haven't already paused me, go pause me now. So remember, I'm putting this in with x's, right? So I'm gonna do second insert, negative. I'm gonna put a +1. That +1 is not inside the log. Down here, this should be a negative 1.3 in parentheses. I have a 2 minus y, but y is really x in this situation, to the 4th. Excuse me. And then plus a y, which is really an x in this situation. So again, I need to graph them. So that's the window I'm looking at. I need to find those 2 points of intersection. So I'm going to do second calc intersect. And remember, although I'm looking for y's in my problem, I know it's the x that matters here. So my bounds, my bounds are going to be x, sorry, not x, fix that. You get on autopilot. Y is approximately 1.23478 ... and I'm going to call that a. And y is approximately, so then so I'm going to quit out before I find that one, right? That's x, and I'm going to store it as alpha a, right? I go back to my graph. I second calc intersect. And I get that for some of you, you're thinking, why is she doing all these calculator steps? It's driving me nuts. And I get that, but some people really, really need them. So if you don't need the calculator steps, you can totally put me on like 2 times the speed or something, and that's great. I don't care. So once I'm here, I quit out, so second quit, right? And then I'm going to go ahead and hit x, which is really y in this problem, and I'm going to store this as alpha b. Cool? All right, so now I found the bounds, right? I have to do the heavy lifting, which is to say that the area that they want is going to be the integral from a to b of, and notice, by the way, it's not a, I found the bounds as left to right, but a needs to be, so a has to be smaller than b, like this is the smaller y value. And that hasn't happened yet where it was an issue, but see how a is 1.23 something and b is 3.27? It needs to be smaller to bigger. If it's not, then you're going to end up accidentally getting a negative area, and that should be a big clue to you that you should go back and erase your work and change your bounds. It doesn't mean erase all your work. It means, oops, I should change my bounds. So I'm going to go ahead and do f of y minus g of y. It really doesn't matter which curve is on the left or the right, to be honest, because of the absolute value, right? So I'm going to do this. Right? And then I'm going to type it in my calculator, and that's it, right? So I'm going to do math 9. I'm going to go to math over to number and pick abs, right? And then I'm going to go to vars, y vars, pick y1, minus vars over to y vars, pick y2, close the absolute value, comma, with respect to x, which again is totally standing in for my y, from alpha a to alpha b. And again, if you get a negative area, then that's a clue that you accidentally reversed the bounds. So because with the absolute value, there shouldn't be any way that you get a negative area unless you accidentally reverse the bounds. The other way to get a negative area is to accidentally do bottom minus top, like do vice versa. But again, with the absolute value, that wouldn't matter, right? Okay, so let's go back to this challenge problem. So you actually technically have a new way to do this challenge problem here. Because if you notice, although when we did it using with respect to x, when we did this with respect to x, there was not a convenient way to do top minus bottom, because at no point are the curve and the line related. But if you did right minus left, you could actually integrate this thing, right? So the problem is that in order to do the right curve minus the left curve, this has to be in terms of y. So you would integrate from 0 to 9, and you would do this line minus this curve. Now, normally that's actually a pretty cool idea. Here it's not great, and the reason I'm going to say it's not great is that it's a real pain to solve this thing for x. You can do it, but it's awful. So we're going to walk through it, right? But here it's not a great fit. Sometimes this is a really smart, totally dope idea. In this instance, it is not a great idea, but I'm still going to walk you through how it would work, okay? So in this instance, it would be easy enough to solve this curve, right? I could solve this curve for x. So y equals negative 3x plus 18. If I solve for x, I get y minus 18 equals negative 3x. I'm going to get a negative 1/3 x plus 6. Sorry, 1/3 y. Come on, brain. So I get a negative 1/3 y plus 6, and that's great, right? So this is my first function. So this is the function, this is the right of the two functions. So this is the right function of y. Great. The problem is that this one's a real doozy to solve for x. So there are 2 ways to solve this for x. One of them is completing the square, and the other one is to use the quadratic formula. essentially by treating the y as a variable. So the two ways to solve this are either to complete the square, which is not wrong but is not super fun, or to do the quadratic formula where you treat y as the constant because y is not an x. Neither of those is super fun. So if you were going to do this, I'm going to walk you through both. So there's two ways to solve for y. Right, there's two ways to solve for y. Option one is complete the square, which is way back to chapter 5.4 of Algebra 2. So option one is to complete the square. What you would do is you would ignore the constant. There isn't a constant, so that's easy, right? So this plus 0, no constant. You'd factor out the -1. You would do this triangle step where you divide this by 2 to get a -3 and then square it. So you added 9, but you didn't really add 9 because this negative, you subtracted 9, so you do the opposite on the outside. So you would get that y is negative x minus 3 quantity squared plus 9, and then you could solve for x. And it's awful, but you could do it. So you could say, cool, y minus 9 equals negative of x minus 3 quantity squared. Divide by the negative, so essentially 9 minus y is an x minus 3 quantity squared. Take the square root, so you're going to get plus or minus the square root of 9 minus y equals x minus 3. And then you're going to add the 3. So 3 plus or minus the square root of 9 minus y equals x. And then you'd have to figure out whether this is the plus or the minus, right? But if you notice, all of these x coordinates are positive, right? So like, essentially, if you, well, they're not all positive. Let me rephrase that. So notice here, right, that you can't pick a y. Let's say that we pick y is, oh, actually the easiest way to do this is probably to pick y is 0. Yeah, if we picked y is 0, we should get 0 out, right? So if y equals 0, then x is also supposed to be 0, so we can figure out whether it's the plus or the minus. It's the minus, because 3 plus root 9 would be 6, so that's not it. But 3 minus root 9 would be 0, so that's it. So it's the minus case. So it turns out that after all that, this curve is actually x equals 3 minus the square root of 9 minus y. That's the other curve. This is the left curve. So this is, again, not a great plan here. If you'd done the quadratic formula to get the same answer, you would have done this. Sorry, it was a negative x squared. So the other option, right, and again, I'm not recommending either of these. I wouldn't have done this problem this way. I just wanted to show you it's an option. If you did the quadratic formula, you'd have negative x squared plus 6x minus y. Your a is going to be a -1, your b is going to be a 6, and your c is actually going to be negative y. So you would get that x is negative b plus or minus the square root of b squared minus a 4 times a times c will end up being minus a 4y. All over 2a, right, which would be just a -2. So this ends up being an x equals -6 over -2, plus or minus, and you can take that 4 out, so you get 2 root 9 minus y all over a -2, right? And you'll notice that this actually ends up putting me at the same spot with this answer, because I get x is 3 plus or minus essentially a root 9y, and that's the same answer, and then you go from there. So after all that work, if you chose to do it this way, which again, in this instance would be a horrible problem, you would do right minus left, right? Which again is awful. And if you were doing this without a calculator, it would be pretty hard. But if you're doing it with a calculator, you could literally do this function minus this function in the calculator, which is an advantage that you have only because you solved for y. So the area here essentially would be the integral from 0 to 9 of this function, -1/3 y plus 6, which was the rightmost function, minus a 3 minus a root 9 minus y with respect to y. So a single integral instead of 2 integrals, and if you wanted to integrate it, you could, and you would get the same answer we did. You could also integrate it on your calculator. It's definitely not the better option here, but I want to point out that sometimes when you're handed a challenging problem, there are multiple ways to solution, and had this been an easy solve for y, like it was not, but had it been an easy solve for y, this actually would have been a much easier approach than the way we did it in the other video. Here it was obviously not a much easier approach. Here it was much, much worse. For the record, I will finish it out just because it's not a terrible idea for us to know how to do this. I guess, I don't know, it's probably a terrible idea. So this is going to be a -1/6y squared plus 6y, right? I would distribute this negative probably. So this is a negative, well, I could have just made my life easier and combined those ahead of time. Oops. And then this is technically u sub, where the inside is the 9 minus y. So what's going to happen, so this was actually, let's just make our lives slightly easier for a sec and distribute this negative and make this a negative 1/3 y plus 3, right, because it'd be 6 minus 3, plus a root 9 minus y, right, dy, that's what would be in here. So this is plus a 3y. And then what happens is when I integrate the stuff to the 1/2, right, it's going to be stuff to the 3/2. So I'm going to end up with a 2/3, right, stuff to the 3/2. But the trick is that since the stuff is negative, I'm going to end up with a negative in front here, because if I were to differentiate 9 minus y, I'd end up with a -1 each time. So I'm going to get this evaluated from 0 to 9, which is disgusting. I get it. It's no fun. If I then plug in, I'm going to end up getting that this is a -1/6 times 81, fun, plus a 27, minus 2/3 times, hey, at least that's a 0, right? So yay. And then, but you have to be careful, because when you plug in the 0, not everything gets knocked out. Both of these terms get knocked out, right? But this is a -2/3, 9 to the 3/2, which is not a 0. So that's still a number that we have to deal with. So let's finish this out. I know it was a long problem. So from the 81/6, right, I could cancel a 3 from that and make that a -27/2, right, plus 27, right? And then over here, 9 to the 3/2. Remember that 9 to the 3/2 is the same as the square root of 9 to the 3rd, right? So that's a 27. So, because it's 3 to the 3rd, so that's 27. So I'm going to get that this is plus 2/3 times a 27, right? Well, that's a -27/2 plus a 27, plus what I'm pretty sure is an 18, right? So I think I get 45 minus 27/2, which should be 90 minus 27 all over 2, right? Which should be 63 over 2. Not sure if that's what we got the last time. It's good to check, I suppose. I could have done something stupid, and I'm sure I did, but that's kind of where we land. I don't remember getting a 63 over 2, but I don't have the slide open now, and it's too hard to remember for sure. If we were, that's also assuming that I completed the square correctly, which I think I did. But we can check this on a calculator and see if we get 63 over 2, because again, I don't remember getting a 63 over 2, but it's quite possible. If we were going to check it on a calculator, we could do this minus this, and plug in x's and y's. So if we want to check this on a calculator, we would do math 9, right? Oh, I don't really feel like, hang on, I don't feel like dealing with these functions. We're going to type them in the calculator. So I'm going to do -1/3. And again, if you've tuned this out and said, hey, challenge problem, you're not my jam, I get it. That's okay, but I'm going to see it through. So that's frustrating that I accidentally deleted that. Silly clear being right next to the button I needed. All right, so 6. All right. All right, so that's the first one. And then we have a 3 minus root. And remember, we're using x even though we mean y, because that's how we have to put this in our calculator. So that's right. Okay. And then I'm going to quit out of that, right? And I'm going to go ahead, and I could actually cheat a little if I wanted and go use the last one that I did, but I'm not going to. So math 9, right? I know it's this minus this, so that's going to be my y1 minus my y2, although again, I could cheat and use the absolute value if I didn't know that, right? With respect to x, which is standing in for my y, from 0 to 9, and we'll see if we did something crazy. Hey, there it is, 31.5. So it is, in fact, a 63 over 2. So there we have it. And notice that your calculator doesn't actually get the exact right answer. It gets an approximate answer because your calculator is not actually integrating. You can do stuff that your calculator can't. That's the end of this video.